In question number 33 on page 82 of HCV volume 1, we are given 3 blocks, out of which one of them, M dash, is a triangular block, and we are supposed to find what is the mass of this block, the value of M, capital M, so that this block does not slide on the surface of this block. All surfaces are given to be frictionless, so there is no friction anywhere, including at the pulley, and the pulley is given to be massless too, so it's massless and frictionless, and the string is given to be massless. The word light, we usually interpret it to be light enough to be considered massless. Now, in the absence of the string, you can imagine that if the string is absent, then what would happen is, remember, there is no friction present anywhere, so small m would tend to slide down on the hypotenuse of this triangular block, and at the same time, to maintain the x coordinate, that is the horizontal coordinate of the center of mass, the block M dash would travel towards the left. So that sort of motion would take place, but you are sure that small m would slide relative to M dash in the absence of the string. Now, the presence of the string and the fact that it is connected to capital M at this end makes a difference. You can see that capital M will actually travel down, and it would pull M dash with it towards the right with the same acceleration. And if you consider the situation in the reference frame of M dash, which is an accelerating reference frame, remember, it means it's a non-inertial reference frame. So that would mean that as viewed from this reference frame, this M, small m, would experience a pseudo force in this direction, which is the direction opposite to the acceleration of M dash in the ground frame. And it is this pseudo force which can possibly prevent the sliding of small m on capital M dash. So, for example, if the acceleration of capital M is, let's say, it's a in the downward direction, which would mean that M dash would also accelerate with a in this direction. Now, all these figures are in the ground frame. Okay. Now, let's go to the frame of M dash. So, I'll just rub out these accelerations, and I go to the M dash frame, where M dash itself is unaccelerated in this reference frame. In fact, M dash is at rest, and what would happen is small m would get a pseudo force which is given by small m into that acceleration a, which we just wrote earlier, the magnitude of that acceleration. So if ma in the reference, see, in the we are in the reference frame of the triangular block, if ma is just right, just of the sufficient value to prevent m from sliding either up or down, so this force is going to ensure that m is stationary. But in what reference frame? In the reference frame of the triangular block M dash. If that is the case, it would mean that this a, which is the acceleration of M dash in the ground frame, should be of the exact value, so as to ensure that this happens. So, for example, if we can find what is the force required to keep M stationary on M dash in the M dash frame, then we could equate that force with M into A, and that might be a method to find A. And once we get A, then it's possible that applying Newton's laws of motion, we might find M. So let's try to do it. So let me first just clear things up. I'll just give you an example. Supposing that there is a block, there is an inclined plane, let's say, okay, inclined plane, and it's fixed to the ground. So this is a reminder of a result which we have done earlier. And let's say that there is some block over here. It's not necessarily a rectangular block, and let's say that the block is of mass m. This angle is theta. Now we know that if we apply a horizontal force P, then for small m to remain in equilibrium, P should be in the range mg tan of theta minus alpha and mg tan of theta plus alpha. That's in the presence of friction, that is if the inclined plane is rough. And alpha of course would be the angle of repose, tan inverse of mu s. Now in the absence of friction, supposing that there's no friction, mu is equal to 0 between the inclined plane and the block m, then we have done this result. We have proved it independent of this formula, but you can use this formula to memorize the result. What would happen is, if mu s is equal to 0, it would automatically mean that alpha is equal to 0, because alpha is tan inverse of mu s and tan inverse of 0 is equal to 0. So it would mean P should belong to, in order that the block M be in equilibrium, P should have a minimum value of mg tan theta minus 0, so alpha goes away, and a maximum value of mg tan theta plus 0. So mg tan theta is the minimum as well as the maximum. So the implication is very clear. P should be exactly equal to mg tan theta. There's a unique value because the minimum and the maximum values of P match. So in short, in the absence of friction, if this horizontal force P is to hold the block M in equilibrium, then its value should necessarily be mg times tan theta. And remember, we are assuming that there is no toppling, so the line of action of P is adjusted in such a way that toppling of M doesn't happen. Now we can use this result in the given situation. So you just once again imagine that you are in the reference frame of M dash. I'll just draw the reference frame, and in this reference frame M is of course stationary. That's the condition given in the question. So the pseudo force which does act on M, for the reasons that we just stated, must be, I'll call it P again, that must necessarily be mg times tan of theta. Remember, in this problem I'm not clubbing together the pseudo force with the weight, and I'm not trying to evaluate G effective. So this G is the G which arises because of the real weight, the real gravitational acceleration. So to make this point clear, if I draw the FBD of the figure on the block on the right, the forces are mg in this direction, downward direction, and there's a normal reaction which is perpendicular to the inclined plane, and there is this third force P which is equal to mg times tan theta, and it just manages to hold the block in equilibrium. And likewise, in the given situation on the left hand side, the forces acting on the block M in the reference frame of M dash are, so there is a real force, there's no doubt about it, the weight of the block which is mg in the downward direction, and there is surely a normal reaction N1. The arrows are not to scale, and there is a pseudo force, you are sure of that, which we have called P. So even before identifying it with mg tan theta, you just compare this FBD with the one on the right. And another common feature is that M is stationary on the incline in both cases. So directly you can do it by analogy. So that's what I meant when I said don't try to find, I'm not trying to find G effective in this particular problem. So whether to use the concept of G effective or not, that would depend on the problem. You have to figure out on a case-to-case basis. Alright, so you have this P which is equal to mg tan theta, and do we know what is P? Well, we just said that P is also equal to, well, it's the pseudo force, so it is basically equal to m times the acceleration, the magnitude of the acceleration of capital M dash, that is our reference frame, in the ground frame. So just bear in mind what is A. You keep it in mind, and we'll use that particular information in the next part. So if MA, which we know to be the pseudo force's magnitude, is equal to mg tan theta, then small m will not slide with respect to capital M. Now that immediately tells you that M dash in the ground frame must have an acceleration of g tan theta, of course towards the right. Okay, so how would you generate that acceleration? Well, we generate it in this question by another means because there is a string, etc., but you could do it this way also. You just apply a force on this, okay, and the block M is kept on that. So if you manage to choose the magnitude of the force such that you get an acceleration of M dash to be equal to g tan theta, then you can be sure that this block M will not slide upon M dash. So how you get the acceleration, that's all, it depends on what you have. You can push the block, or in this case you can connect the block to another block through a string, but the acceleration has to be g times tan theta. And now it's very simple. What you can do is you just go back to the ground frame again. So I'll draw my reference frame here, and the situation now in the ground frame is that capital M moves down and its acceleration is equal to A, and since small m doesn't slide with respect to capital M dash, so this M and M dash are going to slide as one block, and of course their acceleration is going to be A towards the right. And we also know the value of A, so A is g tan theta. So this is a question asked in reverse. Usually in Newton's laws of motion questions, the masses are known, the forces are known, and the acceleration is asked. But here the acceleration is known, we have found it out by some method, and we want to find what is this mass. So we want to find what is M. Now of course you have to do the problem in more or less the same method. You just set up the FBD of capital M. So there's going to be a force mg, its weight. Remember, we are in the ground frame, so don't even think of any pseudo forces. And there is a tension in this string T, and the same tension of course travels over here. So we are now drawing the FBD of small m plus M dash. It's considered as a single block because they move together, and you have the weight in the downward direction, which is M dash plus M times G, and you have a normal reaction. Normal reaction is in the upward direction. The arrows are not properly placed, so the line of action I have not considered it in this problem. Is not needed because I'm assuming that toppling doesn't happen. So this normal reaction must necessarily be equal to m dash plus m times g, because the vertical forces must balance. So after this it's very straightforward. You just apply Newton's laws of motion to, first of all, apply it to capital M in the downward direction. So the downward force is mg minus t, and that must equal the mass times the downward acceleration. You can substitute the downward acceleration as g tan theta here itself. That's my equation number 1. And then you apply Newton's second law, sigma f is equal to ma, to this composite block m plus m dash in the rightward direction. So the rightward force is T, and that must equal the mass times, mass is m dash plus m, times the acceleration, which is g tan theta. That's my second equation. Now you solve these two equations, you can eliminate T and you can find m. So very simply you can just add them. So when I add them, this minus T and this T they get cancelled, and I get mg equals mg tan theta plus m dash plus m times g tan theta, and you collect together the m terms on the left hand side. So you get mg times 1 minus tan theta equals m dash plus small m times g tan theta. The g term gets cancelled, and you get m equals m dash plus m times tan of theta, this divided by 1 minus tan theta. And I can convert it into the answer given at the back of the chapter by dividing the numerator and the denominator both by tan theta. So this tan theta gets cancelled, and in the denominator 1 upon tan theta can be replaced with cot theta, and tan theta can be replaced with 1. So m dash plus m the whole upon cot theta minus 1 is the value of m required to satisfy the conditions given in the problem.